Okie doke, we're about to find the field due to a frisbee, a disk, which has charge Q, radius R, but it's a solid disk. And so I will draw the axis. And of course, we're only going to find the field at a point on the axis of said disk. And I'm going to call it the x-axis, and I'm going to put point P out here just to be different. And I want to find the field at that point due to the charge on the disk. How am I going to do this? Well, I'm going to do this by feeding the disk through the calculus onion ring cutter and cutting this disk into a bunch of concentric rings, like this guy right here, more or less. And these are all concentric rings of charge. And let's talk about this ring a little bit. Let's see, it has radius little r, as opposed to the radius big R of the disk. And it has thickness. This is a, just remember, this is the red thing here is a ring. Now, I hope I've been using that word, not a disk. And it has a thickness, so from the outer edge to the inner edge, and I'm trying to draw a little arrow thing here, which you really can't see, is dr. All right. And this ring has a charge dq. Okay, how much charge is that? Well, it's the amount of charge on it. The larger rings are going to have more charge because they have more stuff on them, and the more stuff has more charge on it. So I want us to think about how this charge is spread out on the disk. So we're talking about area charge density, sigma, which is Q over area, because that's going to determine how much charge I have on each of these rings. Let's see, and that is going to be Q over, so this is sigma for the whole disk. Area of the whole disk is pi big R squared, so that's sigma, big Q over pi R squared. The amount of charge on one of these individual rings is equal to the area charge density times the area of that ring. And the area of the ring is how much stuff, how much paint I would need to color this in. All right, so how much area does the ring have? Well, the ring, as we know, is a rectangle. And because if you cut it, you can straighten it out. And here's the rectangle you get if you make a cut there and then just straighten it out. And the rectangle has a length, which is equal to the circumference of the disk, which is 2 pi times little r, and a thickness top to bottom of dr. So the area, the charge on it is sigma times the area, and the area is 2 pi r dr. Okay, that's the charge of the disk. Now, what is the field I'm sorry, that's the charge on the ring, my bad. What is the field that ring creates at point P? Okay, this ring of charge creates a field at point P dE, and I know that because I know the field due to a ring we just found in the last video is, do I remember this, K times Q of the ring times x, how far you are from the center of the ring, times x squared plus big R squared to the 3/2 power. That's the field. Okay, I just mixed metaphors. That's the field that's the big field due to a big ring. Get rid of the D. And the field due to this little this infinitesimally thin ring, which has a charge dq, would be dE, and the q up here would be the charge on the infinitesimally thin ring, which is dq. All right, so that's the field due to one of these rings. And we don't have to do with components in this one because that field points axially along the x-axial is. And so all I have to do to find the total field is to integrate up the field of the elements from all these rings. So I say E at point P is equal to all these suckers added up. And what am I adding up? I'm adding up dE, which is K. K times x times dq. And I'm going to start right off by, instead of writing dq, I'm going to write what dq is down here, which is sigma 2 pi r dr over x squared plus, okay, I already screwed up, because back up here, I wrote this as big fat R squared. That's wrong. I hope you caught that. And because that is this is the field created by one of these individual infinitely thin rings, they all have varying radiuses, and so that r there is actually plus little r squared. Sorry about that. Okay, so down here I'm integrating k dq, kx dq over x squared plus little r squared to the 3 halves power. Okay, is that right? Boy, I hope so. So have I satisfied that I have one variable and d that variable and everything else is a constant? I believe I have. X is a constant for this particular problem. Of course, this is x right here from the center of the range of point P. That's a constant for this problem. Sigma is a constant, 2 is a constant, pi is a constant, k is a constant. There's x is a constant again. So the only variable is r. So now I just have to integrate this with respect to r. Cake. Here we go. And I will also introduce constants of integration, because I'm going to integrate from the smallest r, which is 0, to the biggest radius of a ring, which is big fat R, the radius of the whole thing. Okay. K, and I didn't leave myself room to pull out the constant, or did I? No, I didn't. So I'll do it in a second. So I have, I'm going to write them all out in the front. K, x, sigma, pi. I'm going to leave the 2 there because I want it. And I have 2r dr over x squared plus r squared to the 3 halves power. Okay. All this junk right here is constants. I can pull them out, and I will do that. E is kx sigma pi. Integral of 2r dr over, I'll write it down, 2r dr over x squared plus r squared to the 3 halves power. I see a u du substitution coming up here, and let's see if I can pull this off a little more smoothly than I did in class the other day. I'm going to let u as a function of r equal x squared plus r squared. Therefore, du dr is 2r. Therefore, du is equal to 2r dr. And I neglect to put the limits in, but as I think I mentioned in class the other day, I am a lowly slime dweller and only put them back in at the end. I don't transpose the limits into the u function because it's hard and I don't like doing it. Okay. So what do I have here? I actually have here an integral I'm going to do in blue of du to r dr over u to the 3 halves power. And that integral is, this is where I screwed up the other day, is negative 2u to the negative 1 half. Yes, 1 over n plus 1, u to the n plus 1. Good. And so, so now I can come back here and say in green that the electric field at point P is kx sigma pi times the integral of this stuff is this, and that becomes negative 2u, which is x squared plus r squared to the negative 1 half, and now I'll put in my limits of 0 to big fat R. So, what do I end up with? Kx. And at some point I've got to sub in for sigma, which is, I'm going to go back up and look, q over pi big fat R squared. So sigma is q over pi big fat R squared. I've got a pi. Looks like they're going to go bye-bye. And then I have a 2 in here that I will pull out and throw in here somewhere. But for some reason I want to leave the negative sign inside. And so I'm going to have negative, okay, my variable here, we have to be careful. X, remember, is the constant for this particular problem. Little r is the variable because these rings all have different radius, so that's where I'm plugging in. So I have x squared plus big fat R squared to the negative 1 half minus, and now this time I plug in 0, x squared plus 0 squared, got to square that, to the negative 1 half, done. And so, oh, oops, minus a negative, because I left my minus in there. Oh, Kotz, you're good. Okay, so minus a negative that. should have pulled it out. Okay, so electric field at point P is equal to, my pi's go bye-bye, and I have, this is really neat and tidy, K times X times 2Q over R squared. Oh, and inside here I have, this is 1 over X on the right, and it's negative and negative, and it's X squared to negative 1/2, so that's 1 over X, this whole term, and then minus 1 over X squared plus big R squared, all to the 1/2. And that is that. Yeah. Okay. Good. Done. See you.